Random parameters. Uncertainty. Low data. Credible intervals. Bayesian inference. Ah!
Hello. What's up, dude?
Oh, hey Stan. Well, I'm trying to learn this Bayesian inference stuff you told me about, and I'm just getting really stuck. Do you know anything about conjugate priors?
Oh yeah, don't learn about conjugate priors. That's not going to help you with your project. Have you seen Rick's YouTube video?
No? Who's that?
Oh, well, he's got a great tutorial on the basic theory of Bayesian inference. Search for AFL games on YouTube.
Okay. Let me see. AFL gains. Bayesian inference. I think I found him. Is this him? Stan? Stan? Welcome back to the second video in this series on Bayesian inference with Stan. In this video, we'll go through the basic mathematical concepts you'll need to get up and running. But before we begin, why is Bayesian inference hard to learn for beginners? In my opinion, it boils down to four things. Firstly, I think there's confusion about the goal of Bayesian inference. What is it that we are actually trying to do? Secondly, Bayesian stats has a lot of math in it, the notation of which is very confusing. Too much of that math at the beginning doesn't build intuition. However, removing the math and only focusing on intuition doesn't make it easier to code. The last point is really important because coding is essential to doing practical Bayesian inference. In this video, I'll try to focus on these topics to make it as easy as possible. Every Bayesian inference project has the same three-step workflow. First, like every data project, we start with an input step where we gather data and assumptions. We then go through an equation building step where we derive the equation of the parameterized data generating model called the joint posterior probability distribution. The next step is to sample from this distribution and create a table of samples. This step finds the parameters that most plausibly created the data that you observed. The final step is to use the parameters to simulate the quantities of interest that form our output. The first part of this video will focus on the input and output, which together define the goal of Bayesian inference. The next part will focus on building the joint posterior probability distribution. The third will cover sampling, and the last will focus on simulating the quantities of interest. Throughout the video, we'll be using data recorded from 8 random basketball matches, each row being a different match. The input data X is the difference in the team rating between the home and the away team before the game started. The more positive the difference, the better the home team was than the away team. The output Y is the final margin, which is the difference in points scored by the home and away team. Positive margin means the home team won, and a negative margin means the away team won. Plotting the data as a scatter plot looks like this. It seems that the larger the difference in team rating, the larger the margin to the home team, which makes sense. Along with the data, we need two other pieces of input to start Bayesian inference. The first is the process model. This is a mathematical statement that describes how the Y data was generated, typically based on some unknown parameters theta and the input data, x. For our problem, we have assumed that the rating is linearly related to margin and that our model has two unknown parameters, θ0 and θ1, with some added noise, normally distributed with a standard deviation of 2. The last thing you need is some known facts or assumptions about the unknown parameters. For example, we might know based on our experience that θ0 is roughly 3 and likely between 1 and 5, and that θ1 is between -100 and 100, so we would write that down. Now, you might not be able to get as specific as this, but typically you would know at least the order of magnitude of your parameters. If you really don't know anything about your parameters, that's okay, but you still must write it down. The main idea of Bayesian inference is that despite your best guess, you want to use the data to better know θ0 and θ1. To put it simply, the goal of Bayesian inference is to find the best estimate for these unknown parameters informed by the x and y data. In this case, best is the one that is most consistent with the observed data. We'll explore what that means soon. But why do you want to know this? Well, let's now assume that you had figured out what θ0 and θ1 was from the data. Say θ0 was 3.5 and θ1 was 2.5. You can use this information to do two things. Firstly, theta itself might be something of interest. In this case, θ0 represents the average home ground advantage, 3.5 points. Secondly, if you know the thetas, then you can predict new y's if you have new x's. For example, if we had a new game where the difference in rating points was 3, then we could predict the result of that game as 11 points to the home team. For those of you who are graphically minded, θ0 and θ1 represent the intercept and slope of a line that can be drawn alongside the data. The prediction of 11 corresponds to finding the point on the line corresponding to x equals 3. An alternative way of thinking about Bayesian inference is that we want to find the model, in this case the line, that is most consistent with the observed data. Again, we will explain what consistent with the data means very shortly. Having now understood the input and output of Bayesian inference, let's move on to building the joint posterior probability distribution. Let's turn our attention to θ0. When we say we estimate theta consistent with the data, we don't mean a number or a fixed value. In Bayesian inference, we have to think about parameters as taking on a range of plausible values, with some values being more plausible than others. Why? Basically because lots of values can be consistent with the observed data, but some are more consistent than others. We represent the degree of data consistency or plausibility at any value as an arbitrary shape that, as an example, might look like this. Higher values mean more plausible and lower values mean less plausible. We call this shape the probability distribution function because it tells us the probability level of theta being a particular value. For a function to be a valid probability distribution, it has to have two special properties. One is that it's always greater than 0, because probabilities can only be greater than 0%. The second is that it integrates to 1. That is, the area under the curve is 1. This is because when you add up all value possibilities for a particular parameter, it has to equal 100%. We write the probability distribution of θ0 based on the data as this. P, θ0, straight line, data. If you've never come across this notation before, it can look quite confusing, but essentially if you isolate the θ0 part and ignore the rest for a second, it acts just like any other function would. I can pass in θ0 values as inputs and write down the output just like any other function. I've made a table of 3 results in the top right. Let's now dig a little deeper into the notation. As you've seen, the parameter before the straight line indicates the variable that we are describing the plausibility about, and acts just like any other function. Anything after the line tells us what information the probability distribution is predicated on. Other words you'll see a lot of is conditional on, or based on. Graphically, what this means is that the entire shape of the probability distribution changes if I change the data. For example, for the dataset we had, we might get a distribution like so. But if I change the data by, say, adding a new game to our dataset, or maybe looking at a different dataset of games entirely, this can change my eventual probability distribution. This is all to say, the notation tells us that the inferences we are making about the parameters are based on the dataset we had, and only that dataset. In many cases, we have more than one parameter in our process model. In our example, our model had 2 unknown parameters, and in general, we might have n unknown parameters. In this case, we want to find something called the joint posterior probability distribution, which is very similar to the single parameter version, but tells us plausibility levels for combinations of parameters. Here, posterior is a word we use to describe that the inferences are being made after we have considered the data. you'll often hear people using the word posterior as shorthand for joint posterior probability distribution function. Let's visualize the two-parameter posterior. Instead of a line, we have a surface that can be represented as a colored heat map. Lighter colors correspond to higher plausibility values. I can draw the same table visualization as I did previously, moving from coordinate to coordinate and mapping the values of the posterior as I go. The posterior has the same properties as the 1D version. All values are between 0 and 1, the integral, in this case the volume under the surface is 1, and a different dataset will result in a different shaped posterior. For example, a different dataset may result in a banana-shaped posterior, as shown. Again, our goal is to find the posterior specific to our particular dataset. This gets us to the first and probably hardest task of Bayesian inference, writing the equation that defines the posterior. We'll now go through how to do this using our set of inputs. First, let's be explicit about the word data and rewrite the data portion of our notation in terms of x and y. Then we'll use a special rule called Bayes' rule. Bayes' rule tells us that the equation of the posterior is the multiplication of three separate equations. Forgetting the notation for a second, the first term is called the prior, the second term is called the likelihood, and the third is the normalizing constant. Let's now dig into each individually to see how we proceed with the construction of the overall equation. Let's start with the prior. The reason why we call it the prior is because it is a probability distribution we have about our unknown parameters based on our assumptions before or prior to looking at the data. In other words, it is a mathematical encoding of the assumptions that we started with. The prior itself is written as a joint probability distribution that isn't conditioned on the data. Instead, because it is based on independent assumptions, we can separate the prior further into sub-equations, each equation representing individual probability distributions about each parameter. Under each candidate subfunction, we then write our assumptions about each parameter. For θ0, we said it was roughly 3, but probably between 1 and 5. For θ1, it was anywhere between -100 and 100. We then must transform those statements into mathematical distributions. The first corresponds to a normal distribution with a mean of 3 and standard deviation of 2, while the second is a uniform distribution between -100 and 100. Visually, that would look something like this. Now, I've made the steps seem quite straightforward, but in reality, this is one of the hardest parts of Bayesian inference, so don't worry if you're wondering how to do this for other types of problems. Knowing how to encode your assumptions as various types of parametric distributions really comes with experience. That's one of the reasons why I focus so heavily on examples in the next 6 parts of this series, and you'll get lots of experience dealing with different types of priors then. Continuing forward, then it is simply a straightforward matter of writing out the equations of a normal distribution and uniform distribution with the right parameters respectively, and multiplying them together. After that, we have fully specified the prior equation. This equation looked pretty messy, so mathematicians have invented shorthand versions of these parametric equations to make it easier to fit into a page. Normal distributions are typically written with a capital N, and uniform distributions with a capital U. The notation here follows the convention that we saw before about conditioning. The first term means a normal distribution about θ0 based on a mean of 3 and a standard deviation of 2. The second term refers to a uniform distribution about θ1 based on limits between -100 and 100. Knowing the shorthand version of these distributions is really important, because this is the notation that you'll need to use when using Stan. So we can now substitute our prior equation into our posterior, like so, and then move on to specifying the likelihood. Personally, I think the likelihood is quite a hard concept to grasp, so I'll go a bit slower here. The intuition behind the likelihood is that it is a function that represents the plausibility of observing the data that you did for a given set of specified parameters. Let's go through the derivation to see how this works. Unlike the prior, where we had a subfunction for every unknown parameter, the likelihood has a subfunction for every data point. We have 8 data points, so our equation will be made up of 8 subfunctions. Luckily, these subfunctions only differ by the data that you put into them, so we only really need to understand how to derive one of these. Let's take the subfunction for the third data point. We imagine that y2, the margin of the second game, is drawn from some probability distribution, represented here, where the equation of that probability distribution is the subfunction. That is, it is the probability distribution of y2 after knowing x2, θ0, and θ1. Because we already know what x2 and y2 are, this eventually turns out to only be a function of the unknown parameters θ0 and θ1. For now though, we'll pretend we don't know y2 and x2 and keep them as symbols so you can see how this extends to any pair of x and y. So how do we know which distribution our y2 comes from? That is informed by our process model, which is shown here. Our process model tells us that y2 is linearly related to x2 with some random noise added. Our process model tells us this noise is drawn from a normal distribution with a mean of 0 and a standard deviation of 2. An equivalent way of writing this is that y2 is distributed normally with a mean that linearly varies with x and a standard deviation of 2. As a side note here, at the end of the day, your process model must define a probability distribution of y. For regressions, this isn't usually a problem because of this noise term, but it is a good thing to keep in mind for your own project. Up until now, we haven't really talked about this tilde notation either, even though you see this a lot in the literature. The tilde notation is actually just another shorthand for writing a probability distribution equality, like so. We can now say that the probability distribution of y2, given the parameter mu, is a normal distribution with a mean of mu and a standard deviation of 2. We can be even more explicit and substitute mu with our equation for mu as a function of x, θ0, and θ1. Finally, on the left-hand side, we can simply replace mu with a list of x, θ0, and θ1, since mu is a function of those things. Let's now replace the shorthand capital N with the actual equation this n represents. Even though this is a complex equation, we can see how this is a function of θ0, θ1, x2, and y2. Again, since we have already observed y2 and x2, we simply substitute them into the equation to get a function that only varies with θ0 and θ1. Let's now return back to the shorthand. The derivation we have just done applies to every pair of x and y, every row in our data table. So we simply construct the likelihood sum functions for each data point and multiply them together to get our full likelihood. Substituting this into our posterior yields a pretty long and complex equation, albeit slightly better with the use of this simplifying notation. Up until now, it's been quite a mechanical exercise of substituting variables and making equations. Let me now try to give you some intuition on why all of this works. To do this, let's zoom in on the first term of the likelihood. For a given pair of values, θ0 and θ1, this equation produces a single number. That number describes the plausibility of observing the number 3 under the assumption that the number 3 came from a normal distribution, with a mean governed by a linear combination of θ0 and θ1, dictated by the value of x2, which in this case is -2. And as θ0 and θ1 change, that plausibility number will also change according to how the mean of the normal distribution changes under the linearity assumption. In other words, this equation describes how the plausibility of observing y equals 3 changes as we change θ0 and θ1, given that x equals -2. We can plot this plausibility number and how it changes with θ0 and θ1 on a two-dimensional heat map, shown here. Lighter values correspond to parameter pairs θ0 and θ1 that are most consistent with observing x equals -2 and y equals 3. In this case, θ0 around 5 and θ1 around 1 is the most consistent. We can draw the same surface for a different data point. In this case, the data point has x equals 1 and y equals 4. θ0 of around 2.5 and θ1 around 2 is most consistent with that observation. In the likelihood, we multiply these two surfaces together, so let's go ahead and do that. We end up with a new surface where the highest probability values are now concentrated in the mid region. θ0 is around 3.5, and θ1 is still around 1. These are the theta's that are most consistent with jointly observing the pair of data points previously. We can continue in the same manner, multiplying the distribution surfaces of more data points. We can see that as we get more data points, the plausibility values become more concentrated and vary less with each subsequent function. After all 8 surfaces are multiplied together, we get a nice concentration around θ0 of 3.5 and θ1 about 2.5, as being the values most consistent with observing the data under the assumed process model. Now at this point you might be wondering about the prior. The prior is also just a function of θ0 and θ1, and also represents a surface, so we can multiply its surface to the likelihood, completing the posterior, and observe a very minor but still noticeable shift in the location of the plausible values. This behavior demonstrates a really important point. The prior simply acts like another data point. Its influence in the overall posterior is to shift the posterior to more plausible values. This time, however, it shifts it to values that are more consistent with the assumptions and not with the observed data. Hopefully those two outcomes are similar though. One interpretation of this is that the prior allows your assumptions to become like another data point, and is a formal mechanism to encode known knowledge into your modeling approach. The last part of the posterior is the constant. The constant simply ensures that the probability distribution is valid and integrates to 1. However, it doesn't actually depend on either θ0 or θ1, so it doesn't affect the shape of the posterior at all. As you saw from the last section, we really only need to know the shape of the posterior to understand the properties of the posterior, namely the sections that have the highest probability density. For this reason, we often drop the constant and replace the equality sign with a proportion sign. That puts an end to our posterior equation building section, which admittedly was quite long. Let's move on to equation sampling, which is a much more straightforward task. So let's revisit the posterior equation. This equation is really big if you don't use the simplifying notation, and it looks like this. It's not very nice to work with. But how is this equation related to our final goal, which is really getting an estimate of the parameters individually? For example, at the end of the day, I'd really like a probability distribution function influenced by the data of θ0 by itself. So I could measure the mean or even the standard deviation of it. That's a very good goal, and this individual distribution has a special name called the marginal posterior probability distribution. The marginal posterior is related to the joint posterior through an integration. To get the marginal posterior for θ0, I can integrate over all the unknown parameters that aren't θ0, in this case θ1. Expanding out the equation to its full glory looks like this. Now, I don't know about you, but I can barely integrate anything anymore. Integrating this analytically using symbolic integration is an absolutely not scalable way to do practical Bayesian inference. So we need another method. This is where sampling comes in. Sampling is a way to numerically perform the integral on the previous slide without any of the mess of having to worry about integral calculus. We can illustrate sampling with our canonical problem. Let's overlay the posterior distribution, which we already know, on the coordinate space of θ0 and θ1. Imagine I placed a point in the coordinate space, indicated by this red dot, and recorded where I was. I then move to different locations, say 2,000 more, and record the location of each. Sampling is simply the act of visiting and recording the coordinates of the posterior. Visiting isn't random though. I have to visit coordinates in a very specific manner. That is, the number of times I visit a particular coordinate must be in proportion to the coordinate's posterior probability value. Coordinates with high values, like those in yellow here, I must visit very often, and those in blue, I don't visit much at all. The second task of Bayesian inference is all about recording coordinates of θ in proportion to the value of the posterior at that coordinate. As a side note, the fact that we only need visit points in proportion to the value of the posterior illustrates why we don't need to calculate the normalizing constant from the previous section. You might be wondering why we need to do sampling at all if we have already visualized the full posterior. The answer is that visualization can only happen for very small models with only a few unknown parameters. For larger models, sampling is the only option we have to be able to usefully work with the posterior. After the joint posterior has been sampled from, the resulting table can be very easily used to do statistical inference. For example, to get the marginal posterior distribution for θ0, all you have to do is isolate the θ0 column in the table and draw a histogram. The same thing can be done with θ1. In this case, we can see that the posterior of θ1 is distributed nicely around 2.5. In fact, we can estimate any arbitrary subset of the parameter space by isolating the right columns. For instance, I could entirely recreate the original posterior by taking both columns, plotting them on a scatter plot, and calculating the 2D density estimate. For posteriors with more than 2 parameters, say n parameters, the table looks exactly the same, just with more columns. Clearly, if we can get realizations from the posterior in proportion to their plausibility level, then we can do a lot. But the question still remains, how do you get those realizations in the manner that is proportional to the value of the posterior at those coordinates? Well, this is the fundamental use case for Stan and why it was built. When it boils down to it, Stan is a bunch of C++ math libraries that take as an input an arbitrary posterior equation and the actual data, and spits out sample realizations from that posterior. The algorithm it uses to do this is called Hamiltonian Monte Carlo, and I might make a future video explaining how this works. But actually, you don't really need to know how it works in order to start doing things with Stan. You just need to be familiar with the output that it produces and how to use it. Let's finally move on to the last and simplest step, which is to simulate the quantities of interest. In this section, we'll revisit the output to make sure the connection between the posterior table and the output is clear. Recall that the two main outputs of Bayesian analysis is understanding the parameters themselves and doing future prediction. We've already covered the understanding of the parameters, which is simply the marginal posterior distributions. Let's turn our focus to making future predictions, which I call simulation, but in the literature you'll sometimes see it referred to as the posterior predictive. Let's assume we have a new game where the rating difference x is 3. The goal is to predict a new y. Our process model gives us the relationship between x and y in terms of the parameters and noise, and our sampling has told us the marginal posterior distributions of θ0 and θ1, with means of 3.5 and 2.5 respectively. One strategy could be to take those means and substitute them into the equation along with the new x value of 3. Assuming that the noise takes on its average value of 0, then the prediction will be 11. But this is not a great way to do prediction because A, it doesn't acknowledge the fact that the parameters are correlated in the posterior, which is important for more complex models, and B, doesn't take into account uncertainty levels, which is one of the reasons why we wanted to do Bayesian inference in the first place. To see how to do this properly, let's go back to our joint posterior table. θ0 and θ1 are interpreted as being the intercept and slope respectively of a line in xy space. We can draw the line corresponding to that pair of parameters on a scatterplot overlaid with the actual data, and we can keep doing this for all 2000 pairs to get a distribution of lines. The prediction at x equals 3 can then produce a distribution of predictions from all the pairs, which is the quantity that we are interested in this case. This is precisely what task 3 is all about. Using the samples generated from task 2, simulating any quantity of interest, and then forming a distribution of that quantity. The quantity of interest doesn't actually have to come from the process model itself, and can be any equation that you can think of that uses the parameter values. A helpful way to conceptualize this is that each row in the joint distribution table corresponds to a model realization. That is, a possible combination of the parameters that are consistent with the data. Prediction happens for each of these models, and then gets aggregated together to form a distribution of predictions. To illustrate this with our example, against each row in the distribution, we add a new column with the new x value of 3, and then the corresponding predictions as θ0 plus θ1 times by x new for each row. You might recall this as actually being the definition of the mean of the overall distribution that defines y, denoted with the symbol mu. If we draw a distribution of this parameter, we end up with a normal-looking distribution with a mean of 10.95. To be clear, this says that the mean of the distribution of the mean of y is 10.95. This distribution has a deviation around it of around 2, which is referred to as the estimation uncertainty. The estimation uncertainty arises because the parameters and any deterministic equation thereof is being estimated using a finite sample of data. To finish off the prediction, we need to include the process uncertainty on top of the estimation uncertainty. The process uncertainty is the uncertainty that occurs even with fully deterministic parameters. Again, this is relatively straightforward. We add another column with the process uncertainty E, which is simply Gaussian random numbers with a standard deviation of 2. Adding this to the mean gives us a full prediction of y new. This has a distribution with the same mean of 10.95, but with a much larger deviation of around 5. This larger uncertainty in our prediction arises because of the combined impact of the estimation and sampling uncertainty together. Finally, based on this distribution, our final prediction is approximately 11 plus or minus 5. We've now reached the end of our journey, where we have gone through the entire Bayesian workflow. But since this is a series on using Stan, where does Stan fit into all of this? Well, basically, Stan is a language that helps with all three tasks of Bayesian workflow, from defining the posterior, sampling from it, then generating simulated predictions. In the next 6 episodes, I'll take you through how we do this workflow using Stan on a bunch of different examples. I hope you enjoyed this episode. Thanks so much for watching. If you have any questions, feel free to post them in the comments below, and I'll try my best to get to each of them. Also, if you liked it, give it a thumbs up, subscribe, and turn on the notifications bell. I'll see you in the next episode where we'll start coding.